Hello students. So today we will continue from the last lecture. So in last lecture we looked at the spring basically. So you have a one linear spring and we had node numbered 1 2, yeah, and then we derived a stiffness matrix, then force vector and displacement vector for this system. Okay, so we wrote u1 here, u2 here, then k was the stiffness, and given the force F1 we denoted and F2 we found out the equation was something like this: k 1 minus 1 minus 1 1 and multiplied by u1 u2 is equal to f1 f2. Okay, so this is what we called a stiffness matrix. This is the force vector, displacement vector, and this is what is the force vector. Yeah. Okay, so three things. Okay, now this problem for the spring system we can extend, meaning that extend means we can look at actually the different kind of problem. So let's see. Okay, so let's now look at entirely different problem. We denote like this only, but now we are talking about resistance. Okay, so let's say this is resistance R, and we have voltage here, let's say 1 and 2. So 1 and 2 voltage here, let's say V equal to 0 or V2 equal to 0, and we have V1 equal to, let's say it's a V. Okay, so potential difference delta V is equal to V1 minus V2 equal to V, and there will be a current entering that node here. So let's call this will be I, let's call it I. Okay, so I. So our equation we can write from Ohm's law. Equation is simply V equal to IR, and in this case if V is nothing but V1 minus V2 equal to, we can write it as I1 entering here. So this I1 entering node 1, yeah, so I1 entering node 1, as so we will write equal to I1 R, yeah, or simply 1, this equation we can write it as 1 over 1 over R V1 minus 1 over R V2 equal to I1, or we can write it as 1 over R minus 1 over R, then multiplied by vector V1 V2 is equal to I1. Okay, similar thing we will draw next, and here we are going to have, so let's say we draw like this one, 1 2. Now number 1 we are going to earth, right? So delta V equal to 0, right? Say, okay, so we have V1 here, this is V2 here, and then V2 equal to V, let us call it V1 equal to 0 because we have earth it. There will be a current which will be passing through the resistance, this is R, let us call it I2. Okay. So, you know that for this configuration, when you have left end V equal to 0, we have R here and then we have V here, there will be a current passing through it, and you know this is V equal to IR. So, for V in this case, for V is nothing but V2 minus V1, basically we are talking about, equal to IR, we are talking about I2, right, and multiplied by R, or we are talking about minus B1 over R plus B2 over R equal to I2, or we are talking about 1 minus 1 over R, 1 over R multiplied by V1 times B1 V2 equal to I2. So, if you look here, we have one equation here. So, let us call equation number 1, and then we have another equation here, this is equation number 2, and we are going to combine them together, and what we will get from 1 and 2, we get 1 over R minus 1 over R minus 1 over R, 1 over R, V1 V2 is equal to I1 I2. Okay. So, what we get here is a form of the matrix that we saw earlier for the spring system. We can still call this one a stiffness matrix. Regardless of what it is, we will call it a stiffness matrix. This is a displacement vector, although it denotes the voltage or potential of nodal potential, and this one is force vector. Yeah. We will still this equivalent to, or we can call it this way, okay, because we are talking about in general basically. So, not necessarily this definition is only for a structure type of problem. Any kind of problem we can call it a stiffness matrix or displacement vector or force vector, although in this case what you see is some kind of conductance basically, right. So, 1 over R is the inverse of resistance. So, we do not have to say it a stiffness matrix. Similarly, the V1 and V2 are actually the potentials, right, or voltage at those points. So, we can also call voltage vector, but if we call it this displacement vector, still is fine. Similarly, I1 and I2 are the currents, but we can still call it a force vector. We can now seek some kind of problem we can actually solve using this one, and let us say the problem is something like this. Say there are two resistance, okay, here they are connected like this one, yeah, and let us say one connected to earth. So this is the first, always you start with the node numbering 2 and 3. Let us say R1 equal to 5, R2 equal to 3, and then we have some current passing through it. Yeah. So let us say we have some current coming to this one, and that is equal to say 1 ampere. Okay. Now we have to find out what is the voltages, right? So basically we can make a distribution matrix always K U equal to F, where we can make K, this K is made of two individual distribution matrices for the two resistances. So for us K1, right, so this is element number 1, this element number 2. So K1 will be equal to simply 1 over R1, 1 minus 1 minus 1 1, and that makes it 1 over 5, 1 minus 1 minus 1 1. Yeah, let us call it 5 ohms, 3 ohms. So this becomes per ohms. Yeah. Okay. Similarly, K2 will be equal to 1 over R2, again 1 minus 1 minus 1 1. Okay. So this becomes 1 over 3, 1 minus 1 minus 1 1 per ohm. Right. Okay. Now we have to assemble them. So big K will be equal to, big K is equal to 1 over 5 minus 1 over 5 minus 1 over 5, 1 over 5 plus 1 over 3 minus 1 over 3 minus 1 over 3, 1 over 3, 0 0, like this. Yeah. This is K. Okay. Now U. Okay. So U vector is nothing but the U is, so see the equation here. So K times U equal to F. So we are talking about the U here, right? So the U is V1, V2, V3. Yeah. So V1, V2, V3, and what we know from the problem is V1 equal to 0. So we have V1 equal to 0, V2 we do not know, so it's a V2, and V3 we do not know. So we have to find out what the value of V1, V2, V3 is. Yeah. So accordingly we can write here is equal to V1 equal to 0, V2 we do not know, V3 we do not know. So we write like that. Then current, so F equal to currents. So I1, I2, I3. Okay. What is the meaning of I1, I2, I3? So basically I1, I2, I3 meaning is what is the current coming to that. So that really means what is the current coming to 3, which is 1A, what is the current coming to V2 0.2, which is 0, there is no external current reaching there, but here there is external current going. Here what is the current coming to this one. So we also do not know here because it is connected to, we know V1 equal to 0, so this one we do not know what. One thing is there is a current, net current leaving this. So our system is till here, till the node. So there may be current which is flowing from here to the earth which is attached here, right. So that really means we do not know basically we don't know what is the current flowing here, right. Okay. And here there is no connection from outside, so I will be 0. So, we will write here I1 we do not know, it is kind of reaction basically. I2 is equal to 0, yeah. So, I2 equal to 0 and I3 equal to 1 ampere, right, 1 ampere. So, we get what value? We get I1 0 1, right. So, we write here equal to I1 0 1. These are our vector. Okay. Now, next is we are going to write. So, what will we do? Our equation will be this k multiplied by u equal to f, and u has 0 here, right. We have 0 here. So, that really means first row and first column we are not interested, we interested by this multiplied by V2 V3 is equal to 0 1. This is what we are interested in, yeah. Okay. So, our equation becomes then like this. So, we have 1 over 5 plus 1 over 3 minus 1 over 3 minus 1 over 3 1 over 3 multiplied by V2 V3, right, is equal to 0 1. This is what the equation is. And now we can invert. So, V2 V3 V2 V3 is equal to we have, so let us write it 8 over 15 minus 1 over 3 minus 1 over 3 1 over 3 inverse of that 0 1 is equal to V 1 over 3 here 1 over 3 1 over 3 8 over 15 multiplied by 0 1 and divided by the we have to divide by the determinant of this one. So, let us divide it by, we get 8 over 45 minus 1 over 9, okay. Okay, is equal to what we get simply is 0 multiplied by this one. So, we get simply 1 over 3 8 over 15. So, we have 1 over 3 and 8 over 15, okay, and then divided by we get 3 over 45, okay. Okay. So, 8 divided by 45, so that equal to 5 divided by 45, 8 minus 5 is 3 divided by 45, which that really means 15, basically 15. So, this becomes 15 multiplied by 1 over 3 and 8 over 15. So, you get 5 and 8, sorry. So, you get 5 here and you get 8 here, okay, and this is volts. So, what you get? V2 equal to 5 and V3 equal to 8. So, let us check it whether it is correct. Okay. So, your answer, the answer you get becomes equal to excuse me. So, our answer what we get is V1 equal to 8, V3 equal to 8. So, let us check it. We get V2 equal to 5, V3 equal to 8, 5 and 8. Okay. So, go back 5, 8. So, what we get is this equal to 5 and this equal to 8, and which makes sense because current is flowing 1 ampere. So, so potential difference across this resistance is 1 multiplied by 3. So, 3 volt difference from here to here. Similarly, if you say this 5 ohms 1 ampere flowing, so 5 times 1 is 1. So, voltage difference between this and this is 5. So, if this is 0, so this has to be 5 and this has to be plus 3. So, 0, 5, 8, and what's you answer you get is 5 and 8. So, answer is correct. Okay. Now, next what you have to find out? Something which is not known, and what is I, right? You know from the, I mean, even if you are most of you are in mechanical, but still you can see that whatever current entering here should leave here. It is similar to whatever, if there is a spring and there is no other forces applied, whatever force is here, same force has to be here. The similar thing, whatever current is entering here has to leave. So, I1 has to be equal to 1, but again physics we do not apply here, just by mathematics we should be able to get it. So, we already have the metric system, we just have to see, calculate, and we get it. So, we will, that's what we will do next. So, we find out what is equal to I1, means what is the current which is going out of node 1, and for doing that what we to do is we put the value of 5 and 8 here, and then we calculate I1. Okay. So, K multiplied by, here we will have 0, 5, 8 is equal to I1, I2, I3. So, I1 equal to nothing but this multiplied by this, where V2 is equal to 5, V3 equal to 8. But if you see here it is 0 and here it is 5. So, 0 multiplied by 1 over 5, 0 only. Similarly, V3, and here you have 0. So, V3 multiplied by 0 is equal to 0 only. So, what we have is V2 multiplied by minus 1 over 5 is equal to I1 simply, right. So, I will just write here only. So, what we get simply is minus 1 over 5 multiplied by V2 equal to I1, and where V2 is nothing but 5. So, I1 equal to minus 1, and when you say minus sign, that really means it is not entering the node, rather it is leaving the node. So, this is the sign convention for this the current. We have seen that, right, how we have seen on the both the sides. See, when we formulated, right there only we saw, we said I2 is positive when it is entering the node, here also and here also, both the cases I1 is entering. I1 is entering here, which we took as positive. Similarly, here also I2 is entering the node, not leaving the node, which we assume it to be positive. Hence, if we get the negative value, that really means the current is going out of that. That makes sense, because whatever is coming from this side has to leave here, and hence the value what you get is the minus 1 value here, which is correct. Yeah. So, hence we apply the finite element method for electrical system. Okay.